Dr. M.C. Sundaraja. He completed his undergraduate studies from Madurai Kamaraj University and went on to complete his master's in structural engineering from the same. He is a doctorate from Anna University and he's also done his postdoctoral fellowship at the Queensland University of Technology, Australia. He has more than 17 years of experience in the teaching profession and he has also published papers in 39 international journals, 7 national journals, 27 international conferences and 51 national conferences. He has so far published 124 papers in various journals. He went on to receive the Best Research Paper Award from IFERP, a unit of VVERT and NIRE on 4th April 2015. He has also received Outstanding Faculty Award from the Venus International Foundation Faculty Award, VIFFA, in the year 2015. Currently, Dr. M.C. Sundaraja is now working as an assistant professor in Tyagarajar College of Engineering, Madurai.
Welcome to UGC lecture series on B architecture. In the previous lectures, we have seen in detail about the behavior of one-way slab, behavior of two-way slab. In the case of two-way slab, two-way simply supported slab and two-way restrained slab, and also we have seen the behavior of one-way slab. And also we have seen the design guidelines required to design the one-way and two-way and one-way continuous slab. And also we have seen in detail about the reinforcement detailing required for those slabs. Now, in this lecture, we are going to start designing one-way slab using certain worked example. In this, we are going to start with a total load on the slab. When using total load and using the effective span, we are going to find out the bending moment, and using bending moment we are going to find out the effective depth of the slab, and also we are going to find out the reinforcement. That is, in the case of one-way slab, there are two reinforcement, one is main steel, another one is distribution steel. Finally, we are going to check the depth of the slab against the deflection, and also we are going to see the reinforcement detailing of the slab. The first problem we are going to design, that is, design a simply supported flat slab for a room 8 meter and 3.5 meter clear in size. That is, this is a room, it is supported over the wall on all 4 sides. So, the clear size of room is 8 meter by 3.5, this is 3.5 meter. It is supported on all 4 sides. The thickness of wall here it is 230 mm. So, first we need to identify this, whether this slab is one-way slab or two-way slab. That is, Ly by Lx is equal to 8 by 3.5 meter, which is equal to 2.21, which is greater than 2. It is designed as one-way slab. Before that, from the dimension of the room, we need to first identify whether the slab has to be designed as one-way slab or two-way slab. Now, next one, we need to calculate the load acting on its slab, load calculations. In the case of load, there are two types of load, one is dead load, another one is live load. Dead load includes self weight of the structure itself and the weight of partitions and the weight of floor finishes. Next load is the live load which is given in the problem, or we can select it from IS 875 for the respective room of the respective building. I will see the problem. So, here it is supported on 230 mm thick wall and the superimposed load is 3 kilonewton per meter square. Consider other dead loads also. Use M20 and Fe 415 as materials. Draw the section of the slab showing the reinforcement detail. So, we have identified this slab is a one-way slab. It is supported on these two walls along 3.5 meter direction, and this is the cross section of the slab. This is a slab which is spanned along the shorter direction, that is 3.5 meter side, and the thickness support is 230 mm or 0.23 meter. First one is dead loads. Self weight of the slab. In order to find out the self weight of the slab, we need to know the thickness of the slab. The thickness of the slab can be identified or assumed from the deflection limits, that is L y by or L by d ratio. So, here since the slab is supported along the shorter direction, the depth can be calculated from L by d ratio. Here L can be used as 3.5 meter, that is L x by d is equal to 20. So, 20 is for simply supported slab, that is d is equal to L x by 20, that is equal to 3500 divided by 20, that is equal to 175 millimeter. So, we need to use the thickness of the slab for calculating self weight just for more than 175 mm. But based on my experience, I am using, so here d is equal to 175 mm, sorry, L x here it is not 3500, L x is 3.5 meter plus 0.23, that is equal to 3.73 meter, that is LEFF, that is 3730, that is equal to 186.5 millimeter. Center to center distance between the support is called as the effective length of the slab. Here d is equal to 186.5 plus clear cover for the slab is 15, then I am going to use 10 mm diameter bar, or you can use 8 mm diameter bar, that is equal to 205.5 millimeter. So, we can use this as 210 millimeter. I am going to assume the overall depth of the slab is 150 mm based on my experience. We will check it whether this assumption is correct or wrong based on the bending moment as well as the deflection criteria. We will check it. If it is very less, we are going to again redesign the thickness of the slab by assuming somewhat more than this 150 mm. That normally, that is design of concrete structures, normally it is called as trial and error method of design of structure. That is why I am assuming 150 mm, that has been known from the L by D ratio. It has to be assumed as 200 mm, but I am assuming it is 150 mm. Finally, I am checking whether our assumption is correct or not based on limit state of collapse under flexure as well as the limit state of subversibility under deflection criteria. I will check it. Now, first one, self weight of the slab. Self weight of slab is the overall thickness of the slab, that is 0.15 m meter into the unit weight of concrete is 25, that is equal to 3.75 kilonewton per meter square. In the problem, they have asked us to consider other dead loads also. So, self weight of the slab, other dead load is weight of floor finish. Normally, in the case of a building, normally we are providing 1 inch thickness flooring. Here I am assuming concrete flooring, the thickness of concrete flooring is 25 millimeter, that is 0.025 meter, that has to be again multiplied by its unit weight 24 kilonewton per meter cube, that is taken as 0.60 kilonewton per meter square. So, the case of slab, the load must be calculated per meter square. So, assuming that we are designing the slab for 1 meter square, then the same design can be adopted for any meter square of area of the slab. Next, to the floor finish, we are normally constructing the partition. Weight of partition, as per IS 875, the weight of partition is 1.96 kilonewton per meter square. This is as per IS 875 meter square. If you use this weight, the partition wall, thickness of the partition wall should not exceed 150 mm. That is normally we are using 115 mm thick of wall. So, I have taken this as the weight of partition. So, I am including the weight of partition in my design. So, I can construct the partition wall anywhere on the slab. Now, we need to find out what is the total dead load, that is indicated by WD, that is equal to 6.31 kilonewton per meter square. Next, B, live load on the slab, which is given in the problem. Live load on slab is, that is live load is 3 kilonewton per meter square, W suffix L, that is equal to 3 kilonewton per meter square. Now, second, total load on the slab. Total load on slab, W is equal to W suffix D plus W L, that is equal to 6.31 plus 3, 9.31 kilonewton per meter square. This is the total load acting on the slab. Next one is, say we have found load calculation. Next, second one is effective span of the slab. And we need to find out the effective span. Effective span of slab, that is LEFF. Normally, effective span LEFF is equal to clear span plus the depth of the slab, that is the depth of the slab, which is normally here it is 150 mm, that is we can use overall depth, that is effective span here it is 3.5 meter, 3.5 plus 0.15, which is equal to 3.65 meter, or center to center distance between the support, that is clear span plus 0.23, which is equal to 3.23 meter, whichever is less. So, LEF, which is mean normally 3.5 plus 0.23, 3.73, the normal minimum value will be 3.65 meter, 3.65 meter. Now, next one, third one, bending moment calculation. So, using W and L, we are going to find out the bending moment. So, the ultimate bending moment mu, since it is one way simply supported slab, the ultimate bending moment is the moment, that is design moment, has to be multiplied by partial safety factor. The total load is W into L squared is 3.65 square by 8. W L square by 8, that is 23.90 kilonewton meter. This is a bending moment. Now, I am considering, while we find out the bending moment, I need to consider 1 meter width of the slab. By considering 1 meter width of the slab, I am going to find out effective depth of the slab from bending moment. Normally, we are designing the slab for 1 meter square. So, on width, I am considering 1 meter width of the slab. The effective depth of the slab, which is found from by equating mu to mu limit. It means that I am assuming our section is a balanced section. So, mu limit for given grade of steel is 0.138 FCK BD square. So, mu equal to mu limit, which is equal to 0.138 FCK BD square. So, D is equal to square root of mu divided by 0.138 FCK B. So, here B is 1000, 1 meter, that is mu is 23.90, 23.90 into 10 to the power 6 divided by 0.138 into 20 into 1000, that is square root of it, which is equal to, that is 93.06 millimeter. So, we have adopted D is equal to 150 mm, we have adopted small d is equal to 150 mm minus 15 minus 8 by 2, that is equal to 131 millimeter, is correct, which is less than 131 millimeter. Hence, it is safe against flexure, is correct. Next, I am going to keep the D is 150 mm. Since I am going to check this depth against another limit state, that is limit state of serviceability, that is why I am keeping the assumed value, that is D equal to 150 mm, small d is equal to 131 mm. Now, I am going to find out next step, fifth step, area of reinforcement. So, first area in the case of a one way simply supported slab, there are two reinforcement, one is main steel, another one is distribution steel. So, the main steel which is found from the bending moment. So, since we have increased the depth of the slab, this slab which is automatically under reinforced section, normally mu is less than mu limit. So, it is designed as a singly reinforced rectangular, singly reinforced section. So, now I am going to use the formula to find out the AST for a singly reinforced, that is 0.87 Fi AST into D minus 0.416 XU. So, in this XU is equal to normally 0.87 Fi AST divided by 0.36 FCK B, which is equal to, that is 0.05 AST. By substituting all the parameters, XU must be equal to 0.05 AST. I am substituting XU equal to 0.05 in this expression. Mu here it is 23.90 kilonewton meter. 23.90 into 10 to the power 6, which is equal to 0.87 into Fi for the slab is Fi for the steel is Fe 415 into AST into D is 131 minus 0.416 into 0.05 AST. From this, and here I am going to form a quadratic equation AST square minus 6297.4 AST plus 3.18 into 10 to the power 6 equal to 0. By solving this quadratic equation, we can get two roots. Since it is under reinforced or singly reinforced section, we need to select the minimum root, that is AST required for our slab is 553.59 millimeter square. Is correct. This is the AST required. Again, I am going to check this main steel with the minimum steel which is given in the code. Check for minimum steel. Minimum steel, that is minimum AST required for the steel is, if I am going to use the tar steel, it will be 0.12% of cross sectional area of concrete. Cross sectional area, that is 0.12 divided by 100 into 1000 into the depth is 131, effective depth is 131, that is 157.2 millimeter square, which is less than 553.59 millimeter squares. I am going to use the main steel as 553.59. AST required 553.59 millimeter square. So, I am going to use 10 mm diameter bar. I am going to assume I am going to use 10 mm diameter bar. I am finding spacing of reinforcement, that is for 1 meter width of the slab, I am finding the spacing of reinforcement 1 meter into area of 1 diameter of the bar divided by AST required for, it is 141.87 millimeter. So, hence I am adopting, before that I need to check this spacing with the maximum spacing given in the code book. So, as maximum spacing are, one is for main steel, that is a parallel steel which is provided against a bending moment, 3 into effective depth of the slab, that is 3 into 131 is equal to 393 millimeter, and second one is 300 mm, whichever is less. So, the lesser value is 300, which is more than 141.87. I am adopting this as the design for my design, that is I am providing 10 mm diameter bar at 125 mm center to center. So, why I am reducing somewhat less? To avoid the practical difficulties. So, I cannot keep 141.87 in the drawing. To avoid that practical difficulties, I am keeping much less than the design value, that is 125. I am not decreasing very that is higher value, that is I am not going to decrease that into 100 mm, it will become uneconomical. So, I am reducing somewhat very that is 141.87 to 125 mm, it is somewhat economical one. Next one, AST provided. So, here AST required is 53.59. For that I need 141.87 spacing of reinforcement, but I have again further reduced to 125 mm to avoid the practical difficulties. So, from this I am calculating what are the AST I have provided in the design, that is 1000 into pi by 4 into 8 square divided by 125 mm, that is equal to 623.32 millimeter square. So, this is AST I have provided. Next one, distribution steel. Distribution steel is the minimum steel which is distribute the main reinforcement with the proper spacing. It is provided in the perpendicular direction. So, the minimum AST is, I am using 6 mm dia MS bar. For minimum reinforcement for MS bar, it is 0.15 percentage of cross sectional area of concrete, cross sectional area, that is 0.15 divided by 100 into 1000 into 131, which is equal to 175 millimeter square. Now, using 6 mm dia MS bars, spacing of reinforcement is 1000 into pi by 4 into 6 square divided by 175, which is equal to 176 millimeters. Okay. So, provide I am going to again check this with the maximum spacing. Check with maximum spacing. This is a distribution reinforcement that is provided perpendicular direction of main reinforcement. So, the maximum spacing is 5 into effective depth of the slab 5 into 131, that is equal to 556 millimeter. And another criteria, another one is it should not be less than 450 mm. So, here the minimum value is 450, but I have designed as 176 millimeter. I am providing 6 mm dia MS bar at 150 mm center to center. This is the distribution steel I have found. Finally, I am going to check, that is 6th step or 7th step, check for deflection. I am checking the depth of the section against deflection. So, L by D ratio is equal to 20 for simply supported. This has to be again modified by multiplying with the modification factor depending upon the type and area of reinforcement or the stress which is developed in the reinforcement. Now, for this, to find out modification factor from the figure 4 of IS 456, first I need to find out the percentage of tension. Normally, the graph which shows the percentage of reinforcement versus modification factor, percentage of reinforcement 100 AST provided divided by BD. So, AST provided here it is 623.32, 623.32 divided by 1000 into 131, that is 0.46 percentage I have used. Then stress in steel, which is calculated from the formula 0.58 Fi AST required divided by AST provided, that is I have found is 213.77 Newton per millimeter square. So, from the figure 4 of IS 456, modification factor here it is 1.5. Then I can find out the depth, that is equal to L divided by 20 into modification factor, that is 3500, that is the span of the slab, sorry not 3500, 3723 millimeter, 20 into the modification factor, which is equal to 123.33, which is very less than, which is less than 131 millimeter. So, it is more safe and economical design. So, D is equal to 150 mm and mild steel is 10 mm diameter bar at 125 mm center to center, and the distribution steel is 6 mm dia at 150 mm center to center. Now, we need to draw the cross section of the slab. This is the cross section. This is simply supported slab, and the effective span of the slab is L is EFF is equal to 3.723 meter, and the main reinforcement is, this is the main reinforcement. It has to be cranked from the face of the support is 0.1 L, LEF, 0.1 LEF, and this is the distribution reinforcement. This is the arrangement of drawing of reinforcement. This one is 10 mm dia at 125 mm center to center, and this one is 6 mm dia at 150 mm center to center. This is the cross section of slab. Now, we summarize the lecture. So far, we have seen the design of one-way simply supported slab for a span of 3.5 meter. We have designed the thickness of the slab as well as the reinforcement required for it, and also we have seen the reinforcement detailing of the slab. In connection with this, we can also work out this problem. I have given the two problems. We can get in some practice on doing this problem. In the questions, design a one-way simply supported flat slab for a residential building of effective span 3.5 meter. It carries a live load of 1.5 kilonewton per meter square, floor finish of 1.0 kilonewton per meter square, and also partition wall of 1.96 kilonewton per meter square. Adopt M20 grade concrete and Fa415 steel. Draw the reinforcement details also. Design a one-way simply supported roof slab over an effective span of 4 meter required for an institution building. It carries a live load of 3 kilonewton per meter square and a floor finish of 1.0 kilonewton per meter square. Adopt M20 grade concrete and Fa415 grade steel. Draw the section of the slab showing the reinforcement details also. With regard to the references, we can use IS 456-2000, that is plain and reinforced concrete code of practice, and also we can use the IS 875, that is for finding out the design loads for the buildings and structures, and we can also use the handbook for the reinforcement detailing, that is SP 34 1987. And in with regard to the books, reinforced concrete designed by S N Sinha as well as reinforced concrete limit state designed by Ashok K. Jain. Thank you very much.